Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
And let me give one example. We are playing the game. There is my friend who has 6 coins, and he tosses these coins, and he looks at the resulting configurations, and he says yes or no. And he has some kind of rule in mind when he says yes or no. And you're trying to understand his rule. So here is the first coin tosses. No idea. Still not enough information. We need more examples. Okay. I'm completely lost. I don't know. All right. There is some.
Test of intelligence or what?
Yeah, it looks like parity, and it is a parity. So okay, that's an example of learning process, and there is an important notion, which is the list of samples. When we are trying to learn the function, we compose a huge list of samples in our database.
And do you have any assumptions?
There will be assumptions.
Here, I claim he's wrong. It's penalty of the first bit.
Right.
Or minority, that was the...
But actually,
Number of
But it's
zeros
an
greater than
approximation.
2.
Yeah.
Sometimes it is,
Parity of the
sometimes
first
it's
bit is not.
it's an approximation, and there are 2 reasonable hypotheses: the parity of the first bit and the parity of the whole bunch of bits. You take another few samples in the list, and you will essentially rule out one of your hypotheses. Anyway, it's an example. I will give the strict definition on the next slide. So in this,
So we don't know the probability distribution either. Did we know that
there are
coin tosses?
good question. There are several models. In some models, the distribution is known. For example, it's a uniform distribution. In some models, we don't know the distribution in advance, and it can be an arbitrary distribution. In particular,
But the function can be given as a list, simply. Your 2 yeses are the only 2 yeses, or the other are zeros, or the others are no's, and this is the function. So,
the definition that would follow and would explain it.
Okay, let me give the definition. Probably it will clarify the model. So there is some distribution D. It may be known, it may be unknown. And there is this example oracle. And taking samples of the oracle on the distribution D, we have to output a hypothesis H, which is a reasonable approximation in the following sense. With high probability according to one parameter delta, H is close to the unknown constant C with probability up to epsilon. And finally, we are given the following parameters. N is the number of variables in the function. S is the syntactic size, the size of some syntactic representation of the function. For example, if it's a DNF, S is the number of disjunctions. If it's a parity, it may be the number of the length of its parity representation, the number of variables.
So can you explain what the 2 probabilities are for this? The inner one is for future
tests, and the outer one is for the sample.
Yeah, this is for future.
Which one?
I would look at these two parameters in a different way. This says that with probability delta.
But what are the two probabilities there? I mean, there are
One is
two
over-
One,
different
when you say
random-
is over D, what's the outer one over? There's
Oh.
one probability, there's another probability.
All right. This is over D, I guess, and also our learning algorithm may be randomized, but.
Also, the second probability is
Yeah.
actually
And this.
Cannot see this.
I guess both of them are with respect to D.
The outside one is over the draws of the algorithm. Like you
Yeah.
might get massively unlucky and like see the same example every time. So in that case, you couldn't hope to learn. But
And the inside one is about the future, so it says
yeah,
that.
it should be a not equal in the middle.
Yeah.
The
The inside one just says
Yeah.
that H and C are close under D.
So the inside one, in a sense, is not really a probability. You can think of it. It's a measure of distance.
It's a distance
Yeah.
The outside one is the-
between
It is a
function,
problem.
and that's with respect to D to the some power, and this power is the number of samples that we take. So, oops. We can take many samples, and with respect to this probability, we output some hypothesis, and then we measure the distance. And finally, the algorithm is efficient for the PAC learning if it runs in time polynomial in the number of variables, in the size of the unknown concept, and in these error probabilities. So
Let's get it less.
it's the size of the concept. It's the length of the syntactic representation of a concept as a string. All right, if there are no questions, let me define the proper PAC learning. So usually the concept belongs to some class of formulas. It may be DNF formulas, CNF formulas, decision trees, or whatever. Some class of syntactically defined formulas. And the PAC learning algorithm is proper if it outputs the concept of the same nature, if it outputs the hypothesis of the same nature as the unknown concept. And in this work, we are investigating the proper PAC learning complexity of the following syntactic models: decision trees, which are trees in which every node is queried a variable, and then the computation goes according to the value of this variable. DNF formulas, and intersection of half-spaces, which is intersection of linear inequalities. And there is another useful notion of Occam learning algorithm. So there is one general strategy to learn a function. We take a long list of samples of the unknown function. And if we manage to come up with a small hypothesis, with the hypothesis of small size, which is consistent with all samples in the list, then we output this small hypothesis as an approximation, and it's easy to show that it's sufficient for the PAC learning. And indeed, all our upper bounds would use this strategy. All right. If no questions. So let me state our upper bounds. For learning DNF, the algorithm works in time roughly exponential in the square root of n, which is not the best known for learning DNF. However, our algorithm is proper. And for the learning of the decision trees, the running time of our algorithm matches with the previously known algorithm. And once again, our learning algorithm is proper. It gives the decision tree here, and it gives DNF here. And actually, it's the first proper learning algorithms for both models. And
Not that it really matters, but did the O tilde, was the O tilde some function of S as well?
I guess it's quasi.
I mean, so big that it
No,
probably doesn't.
up to logarithmic factors. So it's n to the 1 over 3 multiplied by some logarithmic.
Log of S.
Yeah.
So, okay.
Okay, let me briefly describe the reason why these are the first proper algorithms. So usually in learning theory, when we try to learn a function, we're using Fourier decomposition, and we try to approximate the function as a sum of low weight characters. But it's not clear how to transform this sum of low-level characters in a decision tree or into a DNF. And the nature of our algorithms comes from a completely different notion, and the algorithms are completely different. That's why they are proper.
Can I ask you a question?
Yes?
Do you know what sort of hypothesis was used in the Ernst and Hausler paper?
I don't really remember. Do you?
I don't know. I was just wondering.
It's not a decision tree. I don't remember. In this paper, it's a low degree polynomial.
Yeah.
And also, we are proving some new hardness results for the learning of these models and also learning of threshold. And for all three models, we basically show that there are no proper PAC learning algorithms modular different assumptions. So for this case, we assume that NP is different from RP. There are no automatizing algorithms. For the case of decision trees, we assume that NP is not in deterministic sub-exponential time. And modular these assumptions, we rule out the possibility of proper PAC learning. And that improves drastically the previously known hardness results that almost all of which are either linear or quadratic.
In your case, you can assume that S is larger than N.
Yeah. So in the definition of learning algorithm, it's polynomial in S and N, and we can roughly assume that S equals N.
So these are not due to some examples where S happens to be so small that the things that you prove kind of, it's not because S is so small that s to the omega 1 is still much smaller than n. S itself is large.
Yeah, S should be large. Yeah. All right. So I have stated our results, and now I'm going to give a brief description of upper bounds and lower bounds. So the source of our upper bounds algorithmic paradigms comes from another field of computer science called propositional proof complexity. So what's the proof complexity? Assume that we are given a propositional formula in this form. For all x, this is true. And we are trying to verify that this is true. We are trying to find some kind of witness that would prove that this is true. And a propositional proof system is any algorithm that can check the witness for this formula. And then we say that this witness is a proof that the formula is true. And the question of automatizability of proof systems is about finding a short proof in the given proof system. Assume that we have a tautology, and we know that there is some short proof. Can we find this proof efficiently? Okay, and the main character in this play will be a simple resolution proof system, which takes as input a set of clauses. It has one resolution inference rule, which says if C or X is true, and if D or not X is true, then C or D is also true. And assume that your initial system is unsatisfiable. Then you hope to infer an empty clause. Then you have proved that it's a contradiction, and the set of clauses is unsatisfiable. And there is resolution refutation size is the minimal number of steps to get an empty clause. The tree-like resolution refutation size is the minimal number of steps in which you build a tree. Whenever you infer some clause, you can use it only once to infer the next clause. And the question of resolution automatizability is the following. Assume you know that there is some short resolution or tree-like resolution inference. Can you build another resolution proof which is as small as possible? And there are several non-trivial automatizability algorithms. An algorithm for general resolution allows to find a proof of size approximately exponent of square root n. And for tree-like resolution, it's possible to find a proof of quasi-polynomial size. And there is also one negative result, which says that if NP is not in sub-exponential randomized time, then there is no polynomial-time automatizable algorithm for tree-like resolution or resolution. So it's hard to find some short resolution refutation, even if you know that one exists. And as probably some of you have noticed, we have already seen this quantity and this quantity on one of the earlier slides. And that's not a coincidence. So what we actually are doing, we adopt these automatizing algorithms for the learning purposes. And so let me now briefly describe these algorithms. So in the base of our learning algorithms lies the procedure bounded search that gets the list of samples and some parameter b. And it finds a DNF of width b, which is consistent with all samples in the list. And it's trivial to check whether one exists in time and to the b, because that's the number of different clauses of width b. And now we describe our main procedure search, which gets this parameter b to be assigned later. And it gets the list of samples. And then for every possible variable, it tries to set this variable to 0 and this variable to 1. And it makes several recursive calls. And it checks what procedure will end up first. And assume that on some assignment, this procedure has finished. Then we run the search restricted on the same variable, but the opposite value, and we run it until the completion. So it's easy to see that this procedure search outputs a decision tree, the final nodes of which are DNFs of width b. And now, if we take b equals 0, then this procedure would output a decision tree. And all right, so in order to learn a decision tree, we set b to 0, and we take that many samples in our list. To learn a DNF, we set b to this artificial parameter, and we need to take a larger list of samples. And the rest of analysis copies literally the analysis of automatizing algorithm for resolution and tree-like resolution. So somehow we managed to show that one algorithm in a completely different field can be used for learning purposes, which is somehow curious. All right, so that's all I would like to tell you about our upper bounds. Now, a few words on the lower bounds. We will need the following parameterized minimum hidden set problem. So in parameterized complexity, you have an NP-complete problem and some parameter key, which is basically the size of unknown concept you're trying to find. For example, in our case, we are interested in a hidden set of size k. And the parameter k is supposed to be small. Typically, it's logarithm of the size or even smaller. And in our case, for this hidden set instance, the k is 2. There is a hidden set of cardinality 2. And there is a whole theory about this parameterized problem with reductions and with some complexity classes. However, we need not only to know that it's difficult to find a hidden set of small size, we need to know that it's difficult to approximate the minimum hidden set when we know that there is a small size solution. And for this, we have proved a theorem that modular this assumption, and it actually uses some ideas of Uri Feige and Joe Killian, that modular this assumption, it's difficult to approximate parameterized minimum hidden set with any constant for logarithmic k. And now goes the reduction. So assume that we have a family of sets. Define the characteristic vector of a set to contain ones in the position that correspond to the given set. And let's consider this picture as a list of samples. There is a bunch of positive samples. Each positive sample corresponds to some set in our system. And there is just one negative sample that contains all zeros. And this construction was known before. And it's not difficult to show that the size of the smallest decision tree, which is consistent with all samples in the list, is exactly the minimum hidden set. And by using the hardness, NP-hardness result of the minimum hidden set, it gives some small gap for the size of the decision tree. However, it's not sufficient for our purposes because we have to amplify the gap. And in order to show that there is no learning algorithm, we have to amplify the size from one small polynomial to some large polynomial. And for this, we apply a common trick from propositional proof complexity. Instead of a single bit xi, we introduce two auxiliary variables, yi and zi, such that xi is the sum modulo 2 of these values. And we design a distribution d on y and z in the careful way so that the sum of y and z would equal one of the characteristic vectors of our sets with probability 1/2, and the sum of y and z would equal all zero vector with probability 1/2. And now it's not difficult to show that the size of the minimum decision tree, which is consistent with not consistent, but which approximates our defined function on this distribution, would be approximately 2 to the k. So on the previous slide, the decision tree complexity was approximately k, and now it's 2 to the k, and we can translate our constant gap into a much bigger gap by this exponentiation. So k is log n, and it's difficult to distinguish parameterized heating set instances with log n solution and C log n, and then it's difficult to distinguish between functions that require decision tree complexity n and n to the c. And that's it. Decision trees are not proper PAC learnable.
You're losing the fact that it's a decision tree rather than, let's say, a branching program where you couldn't do this.
We're using the fact that these are decision trees in this theorem. And also, we tried to prove this a similar theorem for DNFs, what would be natural from propositional complexity point of view, but we failed. So it would imply the following nice corollary. You have a function computed by small decision tree, then it's difficult to approximate it by DNF. It would be nice to prove this, but we have failed so far. Okay, and finally, our last hardness result. In order to show the hardness for DNF learning, we use the reduction from the chromatic number. This is the minimal number of colors to color a graph without conflicts. And once again, we compose the following list of samples. And the goal is to find DNF consistent with all samples in the list. For every vertex in graph G, we introduce a negated characteristic vector, which has 0 in the place of the vertex, and the rest are 1s. And for every h in the graph, we have negated h characteristic vector that has the only zeros in the vertices of this h. All h characteristic vectors are negative examples, and all vertex characteristic vectors are positive samples. The goal is to find the smallest DNF consistent with this list of samples. And it's not difficult to show that the following simple DNF is consistent. Take the colors that color the graph G in the proper way. And for every color set, take the conjunction over this color, and then take the disjunction among all colors. Then this DNF is consistent, and it's not difficult to show that the size of the minimum DNF is exactly the number of colors. And once again, this is a classical reduction towards the DNF learning. And once again, there is a limitation because
so again, the size of the DNF, how do you measure it? The number of...
I measure as the number of disjunctions.
Okay, and regardless of how many variables are involved in each.
Yeah, but the length of each disjunction is n, so it's not a big deal how to measure. It's more convenient to measure the size of DNF as the number of disjunctions. So once again, we'd like to amplify the gap somehow, because for chromatic number, the non-approximability factor is less than n. It's n to the 1 minus epsilon. It's not sufficient for ruling out the learnability. The idea is to take graph products. So for two graphs, in order to multiply them, we take several copies of one graph for each vertex of the second graph, and we take all possible edges between these vertices. And it's known that the chromatic number of the products of two graphs is almost equal to the product of chromatic numbers. And I was said that it's not the right reference for this fact.
They did prove something like this, but maybe it's easier to look at it with the fractional chromatic number and then it's...
Anyway,
Shimonovich maybe from 70s, something like that.
Yeah, so it's probably dated earlier than a lineal Vazirani paper. Anyway, it's a known fact, and let's take the graph product and apply it to this construction. So every vertex in this huge product can be described as a tuple of R old vertices. Every H can be described as a tuple of vertices. Oops, it should be R here, not N. And there is one H in the old graph. So let's apply the same construction for this huge product graph. And indeed, since the chromatic number of the product is almost the product of chromatic number, it will stretch out the size drastically. And there is one slight problem, that now we have too many propositional variables. There is a nice gap in the size in the parameter s, but n is huge, and it's not sufficient for our purposes. It does not yield the non-learnability of DNFs. So somehow we want to take the graph product without blowing up the number of variables. And now recall that the optimal DNF formula from one of the previous slides was monotone. And it gives us a curious idea. Let's encode any variable from this huge tuple in the following syntactic form. Now we have much less variables, and semantically, informally, we treat every variable from this product as a conjunction. Then remember that the optimal formula in this variable would be monotone, and under this translation, it would translate into the monotone DNF formula over these new variables. Of course, that's an informal intuitive reasoning, but I can define the construction formally now. Namely, we introduce new variables xv to the g. So there are nr new variables, which is much less than the number of vertices in the graph product. And now the set of positive examples is the set of negated vertex characteristic vectors in the small graph G, and the set of negative examples can be described this way. So we have all vertex characteristic vectors except one edge characteristic vectors, and all these vectors are characteristic vectors in much smaller space. They correspond to the initial graph G. And it's not very hard to show that the size of the minimum DNF consistent with these new vectors with new samples is still approximately the characteristic number of the graph product. So we managed to amplify the size of the minimum DNF without blowing up the number of variables much. And it takes more efforts to design the appropriate distribution on instances and to prove that in order to approximate under this distribution, one has to use that many disjunctions. But when you know what to get, it's not very difficult to prove it. So we have finished with learning DNFs, low bounds, and now a bit of open problems. So we have shown several connections between different fields of computer science, and it would be curious whether one can come up with more connections. For example, what about applying the known learning theory technique for automatizing the resolution proof system? What's the exact constant in the exponent for the proper DNF learning? There is a better algorithm which does not output a DNF, so cannot be transformed into a proper algorithm. What can be said about proper learning of half-space intersections? That's it. 1 hour, as promised.
Even less. You're great.